Welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 783, titled Minimum Distance Between BST Nodes. In this problem, we'll explore a binary search tree, BST, and determine the smallest difference between the values of any two nodes. Let's dive in and uncover the most efficient way to solve this challenge. In this problem, you are given the root of a binary search tree, or BST, and your task is to determine the minimum absolute difference between the values of any two different nodes in the tree. Let's break this down. The input is the root node of the BST, where each node contains a value between 1 and 100,000, as well as pointers to its left and right child nodes, which could be null if the child doesn't exist. The output is a single integer representing the smallest absolute difference between the values of any two nodes in the tree. This means we are essentially working with the structure of the BST, leveraging its properties to calculate differences efficiently. Let's explore this further with examples. Here's our first example. The given BST has the following structure. The root node is 4, with 2 as its left child and 6 as its right child. Node 2, in turn, has 1 as its left child. To solve the problem, we first extract the values from the BST in sorted order, which gives us 1, 2, 4, 6. Then, we compute the absolute differences between consecutive values, 2 1 equals 1, 4 2 equals 2, and a 6 4 equals 2. Among these differences, the smallest is 1. Thus, the output for this example is 1. The key here is that the BST's in-order traversal naturally provides the sorted sequence of values, which makes it straightforward to compute these consecutive differences. Now, let's look at another example. This time, the BST has a root node of 1 with a right child of 5. Node 5, in turn, has a left child of 3. Again, we retrieve the values in sorted order, which results in 1, 3, 5. The absolute differences between consecutive values are 3 1 equals 2 and 5 3 equals 2. Since both differences are equal, the minimum absolute difference is 2. This demonstrates that the solution must correctly handle BSTs with unbalanced structures, like this one, where nodes are skewed to one side. Here's a third example with a slightly larger BST. The root node is 27, with 14 as its left child and 35 as its right child. Node 14 has a right child, 19, while node 35 has a right child, 44. Extracting the values in sorted order gives 14, 19, 27, 35, 44. The absolute differences between consecutive values are 19 14 equals 5, 27 19 equals 8, 35 27 equals 8, and 44 35 equals 9. Among these, the smallest difference is 5, so the output is 5. This example highlights how the algorithm handles trees with multiple levels and nodes spread across both left and right subtrees. In summary, the problem guarantees that the input is always a valid BST. However, there are specific edge cases to consider. First, when the BST contains only two nodes, the solution must return the absolute difference between their values, as it's the only pair available. Second, in skewed BSTs, where all nodes are aligned to the left or right, the smallest difference will always occur between consecutive nodes in the skew. Third, the algorithm must efficiently handle large values, as node values can go up to 100,000. Finally, when node values are very close to each other, the solution must ensure that it identifies the smallest difference accurately, regardless of the BST structure. These constraints and edge cases help refine the solution and ensure its correctness across a variety of test scenarios. To begin, the brute force approach involves performing an in-order traversal of the BST to collect all the node values in a sorted list. Since the in-order traversal of a binary search tree naturally produces a sorted sequence of values, this step ensures the values are processed in order. Once we have the sorted list, we calculate the differences between every possible pair of elements to determine the minimum difference. However, there's an important observation: because the values are sorted, the minimum difference is guaranteed to occur between two consecutive values. This means pairwise comparisons across the entire list are redundant. While this approach is simple and easy to implement, it is computationally expensive due to the O(n)² complexity of calculating all pairwise differences. This trade-off makes it clear that while the brute force method is intuitive, its inefficiency highlights the need for a more optimized solution. Now, to address the inefficiencies of the brute force approach, we can optimize the process by focusing on the fact that the minimum difference is only relevant between consecutive values in the sorted order. Instead of storing all node values in a list, we can compute the differences dynamically during the in-order traversal. By maintaining the previous node's value and updating the minimum difference on the fly, we eliminate the need for additional space to store the entire sequence. This results in an approach with O(n) time complexity and O(1) additional space, excluding the recursion stack. The algorithm is straightforward: perform an in-order traversal, keep track of the previous node value, and calculate the absolute difference with the current node value, updating the minimum difference as needed. This optimized approach is both time-efficient and space-efficient, though it does require careful handling of edge cases, such as when the tree contains only 2 nodes. When deciding between recursive and iterative in-order traversal, there are trade-offs to consider. Recursive traversal is simpler to implement and more concise, but it uses O(h) space for the call stack, where h is the height of the BST. This can be a concern in cases of unbalanced trees, where the height may lead to stack overflow. On the other hand, iterative traversal avoids recursion and is therefore safer in terms of space usage, but it requires explicitly managing a stack, which can make the implementation more verbose and complex. For this problem, we chose the optimized approach using recursive in-order traversal because it offers a good balance of simplicity and efficiency. By leveraging the observation that minimum differences occur between consecutive nodes, this approach eliminates unnecessary comparisons. Although the recursion stack incurs O(h) space, this is an acceptable trade-off for balanced BSTs, making the recursive method both clean and effective. This chosen strategy effectively balances correctness, efficiency, and implementation simplicity. By focusing on the critical observation that minimum differences arise between consecutive values during in-order traversal, we eliminate redundant computations. The recursive approach ensures the implementation remains clean, while the optimized algorithm achieves O(n) time complexity and O(1) additional space. These advantages make it an ideal solution for this problem, providing optimal performance without sacrificing readability or maintainability. To tackle the problem of finding the minimum absolute difference between any 2 nodes in a binary search tree, we start by understanding the brute force approach. The first step is to traverse the BST using in-order traversal. This method ensures that we visit all nodes in ascending order of their values, thanks to the properties of a BST. During this traversal, we recursively explore the left subtree until we reach the leftmost node, then we visit the current node and capture its value in a list. Finally, we proceed to traverse the right subtree. The reason we use in-order traversal here is that it guarantees a sorted sequence of node values, which simplifies the subsequent step of computing differences between them. After traversing the BST, we store the values of the nodes in a list called sorted_values. This list will contain all the node values in sorted order, making it easier to calculate the differences between consecutive values. Once we have this list, we iterate through it, taking consecutive pairs of values. For each pair, we compute the absolute difference and keep track of the smallest difference encountered so far. Finally, we return this minimum difference as our result. A key insight here is that, because the list is sorted, the smallest difference between any 2 nodes will always occur between 2 consecutive elements in the list. This eliminates the need for a more computationally expensive comparison of all possible pairs. However, while this approach is simple and leverages the BST's properties effectively, it is not the most efficient since it requires additional space for the list and extra computation steps. It's important to note a few additional considerations. For instance, if the BST has only 1 node, there are no valid pairs to compute a difference, so the program must handle this explicitly. Similarly, if the tree is empty, no difference can be computed, and the result should indicate this, such as returning infinity or a null value. The list sorted_values plays a critical role here, as it stores the node values in sorted order and allows for sequential access, which simplifies the computation of differences. In terms of complexity, the in-order traversal of the BST takes O(n) time, where n is the number of nodes, and iterating through the list to compute differences also takes O(n). This gives an overall time complexity of O(n). For space, the auxiliary list requires O(n) space, and the recursive call stack for in-order traversal uses O(h) space, where h is the height of the BST. For a balanced BST, this means an additional space complexity of O log n, resulting in an overall space complexity of O n. Here is the Python implementation of the brute force approach. We start by defining the structure of a tree node using the treeNode class, where each node has a value and optional left and right children. The getMinimumDifference function begins by initializing an empty list called sorted_values, which will store the values from the BST in sorted order. A helper function, in_order_traversal, is defined to carry out the in-order traversal. This function takes a node as input, checks if it's null, and if not, recursively traverses the left subtree, appends the node's value to the sorted_values list, and then traverses the right subtree. The in-order traversal is then initiated from the root node, populating the sorted_values list with all node values in sorted order. Following this, we initialize a variable min_diff to infinity to track the smallest difference. The final step in the implementation is to iterate through the sorted_values list, comparing each pair of consecutive elements. For each pair, we compute the absolute difference and update min_diff if the current difference is smaller than the previous minimum. Once all pairs have been evaluated, we return min_diff as the result. This implementation, while not the most optimal, is straightforward and leverages the properties of the BST effectively to find the minimum absolute difference between any two nodes. This Python implementation effectively solves LeetCode problem number 783, minimum distance between BST nodes. The problem requires finding the smallest absolute difference between values of any two nodes in a binary search tree, BST. The algorithm leverages in-order traversal to extract the node values in sorted order, which simplifies the calculation of differences. ###line-by-line explanation. 1. The min_diff in BST function takes a BST root node as input. 2. Inside the function, a helper in_order_traversal is defined. This recursive function performs an in-order traversal of the BST and appends node values to the values list in ascending order. If the current node is none, the function simply returns base case. Otherwise, it first traverses the left subtree, processes the current node by appending its value, and then traverses the right subtree. 3. The values list is initialized as empty, and the in_order_traversal function is called with the root node and the list. 4. After the traversal, the values list contains all node values in sorted order. 5. The variable min_diff is initialized to infinity, float, inf, to store the smallest difference found during the iteration. 6. A for loop iterates through the values list starting from the second element, index 1. For each pair of consecutive values, the difference is calculated and compared with min_diff. If the current difference is smaller, min_diff is updated. 7. Finally, the function returns min_diff, which holds the minimum absolute difference between BST node values. ###key advantages. Efficiency. The in-order traversal ensures the BST properties are utilized, and the difference computation is performed in linear time. Simplicity. Using a sorted list of values simplifies the logic to find the minimum difference. Edge case handling. The function works for all valid BSTs with at least two nodes, as per problem constraints. This implementation runs in O(n) time complexity, where n is the number of nodes in the BST, and requires O(n) auxiliary space for the values list. It is both efficient and easy to understand, making it a robust solution for this problem. Here, we begin by importing the necessary Java utilities and defining our solution class. The main method, min_diff in BST, is designed to calculate the minimum difference between any two nodes in a binary search tree. To accomplish this, we use an array list to store the values of the tree nodes in sorted order by performing an in-order traversal. The in-order traversal method is implemented as a helper function, which recursively traverses the left subtree, adds the current node's value to the list, and then proceeds to the right subtree. Once all the values are stored in the list, we iterate through the list, calculating the difference between consecutive elements. The minimum difference found during this iteration is stored in the min_diff variable, which is initialized to integer.max_value to ensure it captures the smallest possible difference. Finally, the method returns the minimum difference as the result. The treeNode class is defined next to represent the individual nodes of the binary search tree. Each node contains an integer value val, along with references to its left and right child nodes, named left and right, respectively. The class includes three constructors. The first is a no-argument default constructor, the second initializes the node with a specific value, and the third allows us to set the value along with the left and right child nodes. These constructors provide flexibility in creating tree structures for various test cases, making it easier to build and manipulate binary search trees for the main solution. To solve this problem, we start with a simple binary search tree, or BST, that contains the nodes 2, 1, and 3. First, we visualize the structure of the BST. The root node is 2, with 1 as its left child and 3 as its right child. Next, we perform an in-order traversal, which visits nodes in sorted order. Starting at the root, we move left to node 1. Since node 1 has no left child, we add 1 to the list of values and backtrack. With no right child to process, we return to the rooted node 2, add 2 to our list, and proceed to the right child, node 3. Node 3 has no left child, so we add 3 to the list and finish the traversal. At this point, the in-order traversal gives us the sorted list 1, 2, 3. Now that we have the sorted list 1, 2, 3, we calculate the minimum difference between consecutive elements. First, we compare 2 minus 1, which equals 1. Then, we compare 3 minus 2, which also equals 1. The smallest difference in this case is 1. Thus, the result for this example is 1. Next, let's consider a larger BST with the nodes 4, 2, 6, 1, and 3. Visualizing this tree, we see that the root is 4, with 2 as the left child and 6 as the right child. Node 2 has 2 children, 1 on the left and 3 on the right. For this larger BST, we again perform an in-order traversal to extract the elements in sorted order. Starting at the root, node 4, we move left to node 2, then further left to node 1. Since node 1 has no left child, we add 1 to the list of values and backtrack. After processing node 1's right child, which doesn't exist, we return to node 2, add 2 to the list, and move to its right child, node 3. Node 3 has no left child, so we add 3 to the list and backtrack again. Returning to the root, node 4, we add 4 to the list and proceed to its right child, node 6. As node 6 has no left child, we add 6 to the list. With no further nodes to traverse, the in-order traversal completes, yielding the sorted list 1, 2, 3, 4, 6. With the sorted list 1, 2, 3, 4, 6, we calculate the minimum difference between consecutive values. First, we compare 2 minus 1, which equals 1. Then, 3 minus 2 gives 1, and 4 minus 3 also equals 1. Finally, we compare 6 minus 4, which gives 2. Among these differences, the smallest is 1, so the result for this example is also 1. Now, let's analyze an uneven BST with the nodes 90, 69, 49, 89, and 52. Visualizing this tree, the root is 90, with 69 as the left child. Node 69 has 2 children, 49 on the left and 89 on the right. Node 49 has a single right child, 52. For the uneven BST, we proceed with the in-order traversal. Starting at the root, node 90, we move left to node 69, then further left to node 49. Since node 49 has no left child, we add 49 to the list of values and then process its right child, node 52. Node 52 has no left child, so we add 52 to the list. With no right child to process, we return to node 69, add 69 to the list, and move to its right child, node 89. Node 89 has no left child, so we add 89 to the list and backtrack again. Finally, we return to the root, node 90, add 90 to the list, and complete the traversal. This results in the sorted list 49, 52, 69, 89, 90. Using the sorted list 49, 52, 69, 89, 90, we calculate the minimum difference. First, we compare 52 minus 49, which equals 3. Then, 69 minus 52 gives 17, and 89 minus 69 equals 20. Finally, we compare 90 minus 89, which equals 1. Among these differences, the smallest is 1. Thus, the result for this example is 1. Across all the examples, the algorithm reliably identifies the minimum difference between any two nodes by leveraging the sorted order produced by the in-order traversal. This ensures accuracy and efficiency in solving the problem. To analyze the time complexity of this algorithm, we can break it down into two main components: the in-order traversal of the binary search tree and the computation of the minimum difference between consecutive values. First, during the in-order traversal, each node in the BST is visited exactly once, which ensures that the traversal takes n time for a tree with n nodes. Each visit involves constant time operations, so this part is linear in complexity. Next, after the traversal, the algorithm iterates through the sorted list of values to compute the minimum difference between consecutive elements. This step also takes n time since we are processing each of the n elements in a single pass. When we combine these two parts, the total time complexity becomes n for the traversal plus n for the minimum difference calculation, resulting in an overall time complexity of n. Now let's consider the space complexity. There are two main contributors to the space usage: the recursive call stack and the auxiliary space for the list of values. During the in-order traversal, the algorithm uses recursion, and the maximum depth of the call stack corresponds to the height of the BST. For a balanced BST, the height is log n, leading to a stack space requirement of log n. However, for a skewed BST, where the tree resembles a linked list, the height could reach n, making the stack space usage n in the worst case. Additionally, the algorithm stores all node values in a separate list, which requires n space since there are n nodes in the tree. Combining these two factors, the total space complexity is h for the recursive call stack plus n for the values list. In the worst case, where h equals n, the total space complexity becomes n. Now let's analyze the best, average, and worst cases for this algorithm. In the best case scenario, we have a balanced BST with n nodes, where the height is log n. This minimizes the recursive call stack space, but the values list still requires n space, making the total space complexity n. The time complexity remains n, since we still need to traverse all nodes. In the average case, for a typical BST, the height is approximately log n, so the time and space complexities are the same as in the best case. In the worst case, the BST is skewed, resembling a linked list. Here, the height becomes n, leading to a call stack space of n, and the values list also requires n space. Thus, the total space complexity is n. Comparing this approach to a naive solution, where every pair of nodes is compared, the naive method would take n squared time due to the n squared pairs to evaluate. The current algorithm is far more efficient, leveraging in-order traversal to produce a sorted list, reducing the problem to a linear pass, and achieving n time complexity. Finally, let's solidify our understanding with a mathematical proof of the big O complexities. For the in-order traversal, each node is visited exactly once, and each visit involves operations. With n nodes, this results in a time complexity of n. For the calculation of the minimum difference, the algorithm loops through the values list, performing operations for each of the n elements, resulting in n time complexity for this step. In terms of space, the values list stores all n node values, requiring n space. Additionally, the recursive call stack uses h space, where h is the height of the tree. In the worst case, when the tree is skewed in h equals n, the total space complexity becomes n. Thus, both the overall time and space complexities of the algorithm are n, confirming its efficiency. When working on this problem, there are a few common mistakes to watch out for. First, not considering edge cases can lead to major issues. For example, if you don't account for scenarios like an empty tree, a single node tree, or a tree with duplicate values, your solution might produce runtime errors or incorrect results. It's critical to test these edge cases thoroughly during development. Another issue is improper traversal. Since this problem relies on sorted output, using in-order traversal is typically required. Pre-order or post-order traversals, while valid in other contexts, could lead to incorrect results here. Additionally, overlooking problem constraints is a frequent pitfall. For instance, with a tree size limit of up to 10,000 nodes, a naive brute force approach with n superscript 2 complexity would likely fail for large inputs. Lastly, mismanaging space complexity can be problematic. Storing all nodes in a list, while straightforward, increases space usage unnecessarily to O(n). Instead, more efficient approaches like Morris traversal can achieve constant space complexity. Recognizing these potential pitfalls early makes problem solving far more effective. Another mistake to avoid is confusing a binary search tree with a general binary tree. Binary search trees have specific properties, like sorted order and in-order traversal, but not all problems involve BSTs, many use general binary trees instead. Always verify the problem description to ensure your logic aligns with the correct tree type. Now, for interview preparation, leveraging BST properties is key. The fact that an in-order traversal of a BST provides sorted values can significantly simplify tasks involving comparisons, ranges, or finding minimum and maximum values. When deciding between recursion and iteration, consider the trade-offs. Recursion is often more intuitive for tree problems but can lead to stack overflow if the tree is very deep. Iterative solutions, while more complex to implement, handle deep trees more safely. Optimization should also be a priority. For tighter constraints, advanced techniques like Morris traversal, which reduces space complexity to O(1), or divide and conquer methods can provide significant improvements. Lastly, during interviews, clear communication is vital. Explain why you chose a specific traversal method, such as in order, and discuss the trade-offs you made between time and space complexity to demonstrate your thought process. There are several related problems that can further strengthen your understanding of working with binary search trees. For instance, LeetCode problem 98, Validate Binary Search Tree, focuses on verifying whether a given tree satisfies the BST properties. This requires a careful traversal to ensure all nodes maintain the correct ordering. Another example is LeetCode problem 230, KTH smallest element in a BST, where you utilize the sorted order of in-order traversal to efficiently find the KTH smallest value. Of course, LeetCode problem 783, minimum distance between BST nodes, is the one we're focusing on here. It hones your ability to calculate differences between node values to find the minimum. Finally, LeetCode problem 99, recover binary search tree, requires identifying and correcting misplaced nodes in a BST. These problems highlight how versatile BSTs are and how mastering traversal techniques can be applied across a variety of scenarios. There are multiple approaches to solving this problem, each with its own trade-offs. The brute force approach involves traversing the BST, collecting all the values in a list, sorting them, and then calculating the required results, like differences or sums, based on the sorted values. While simple to implement, this method has a space complexity of O(n) due to the additional list, making it unsuitable for very large trees. A more optimized solution uses in-order traversal directly to process nodes without storing them in a list. During the traversal, you can keep track of state variables, such as the previous node, to calculate results on the fly. This approach is space efficient, requiring only O(1) additional space, but it does demand careful handling of these variables to avoid errors. Lastly, Morris traversal is another alternative for in-order traversal. It reduces space complexity to O(1) by using a technique called threaded binary trees, which avoids recursion or stack usage. However, this method temporarily modifies the tree structure, so you'll need to restore it afterward, which adds complexity to the implementation. Each approach has its advantages and downsides, so choosing the right one depends on your specific constraints and requirements. Great work! To summarize, we solved the minimum distance between BST nodes problem by leveraging in-order traversal to identify the smallest difference between node values in a BST. Key takeaways include the importance of traversal techniques and optimizing for both time and space complexity. Thanks for joining, and be sure to subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!